After studying this model, you shall be able to know more about applications of great orthogonality theorem. You will also know how to construct table of C4V point group, verify the characters of irreducible representation so obtained, construct character table for C2H point group, verify the entries for each and every operation into C2H point group. That is, we will take up on near C4V and C2H point group character table. In earlier models on great orthogonality theorem, we have learned about various rules derived from great orthogonality theorem. We have also learned about the applications of these in connection with the irreducible representation and their characteristics. In this module, you will learn how to use these rules from great orthogonality theorem to construct a unique character table for a point group. Construction of character table of point group. Here we will take few examples and will explain the procedure for finding the complete character table for the molecule in question. And let us take the construction of character table for C4V point group. Which molecule will belong to C4 point group? Let us take very common example of xenon oxy tetrafluoride, HCO4. The molecule has C4 axis, 4 sigma V, 2 sigma P plus 2 sigma D and 1 C2 axis along C4 axis as shown in this over here. Molecule belongs to C4V point group. The total number of symmetry operations generated by these symmetry elements are E, 2C4, C2, 2 sigma V, 2 sigma Ds. These have been divided into 5 different classes. So, according to the rules of great orthogonality theorem, the number of irreducible representation in group equals to number of classes. So, there are 5 irreducible representation into C4V point group character table. The total number of symmetry operation is 8 and thus the order H is equal to A. The format of C4V character table can be shown as, that is, we have C4V, then we list the symmetry operations class wise and then we write in tau 1, tau 2, tau 3, tau 4, tau 5. Since there are only 5 classes, so there will be 5 irreducible representation. This will be the format of character table. Now, these we know again the rules from great orthogonality theorem. The sum of squares of the dimensions of irreducible representation equals to order of the group. Now, let the dimensions of these 5 irreducible representations be L1, L2, L3, L4, L5. Therefore, L1 square plus L2 square plus L3 square plus L4 square plus L5 square is equal to 8. Also, we know the relation, that is summation chi r square is equal to h. This shows that the sum of the squares of the character of E in all irreducible representation equals to order of the group. Relating irreducible and reducible representation will only be satisfied when L1 is equal to L2 is equal to L3 is equal to L4 is equal to 1 and L5 is equal to 2. That is, the dimensions respectively are 1, 1, 1, 1 and 2. For using equation, number of operation in a class must be taken care, because the dimensions of irreducible representation equals to character of E, that is chi E. We take the format of the C4V and we write down the dimensions under E. Tau 1 is 1, tau 2 is 1, tau 3 is 1, tau 4 is 1 and tau 5 is 2. So, we also know that in each point group character table there is always present a totally symmetric one-dimensional irreducible representation for which each symmetry operation has the character as plus 1, and let this irreducible representation be tau. So, C4V character table with this information again can be written in this format. That is, I am writing for tau 1 all the characters as for E and all other as 1, 1, 1, 1. All symmetry operation for tau 1 has the character as 1. So, this is now the present format. Now, since tau 1, tau 2, tau 3, tau 4 are one dimensional, the character for all operation in these irreducible represent will be plus minus 1 only, because they are of one dimensional. They can be either plus 1 or can be minus 1. Let the character of these operation in tau 5 be plus minus chi C4, plus minus chi C2, plus minus chi sigma V and plus minus chi sigma D. So, the format of the character table for C4V now becomes as, that is, for tau 1 all characters are 1, for tau 2 for E is equal to 1, and rest of them I am writing as plus minus 1, plus minus 1, plus minus 1, plus minus 1. And for tau 5 the characters are 2 and then plus minus like this, C4, C2 like this. So, this is the format of the table, and now we have to find out the values of chi C4, chi C2, etc. In a class, the square of the characters for the symmetry operation when multiplied by number of operation in that class and summed over all irreducible representations equals to order of the group. Let us take C2 class and apply this rule down the column. 1 square plus plus minus 1 square plus plus minus 1 square plus minus 1 square plus minus chi C2 square, that is 8. And this is 1 plus 1 plus 1 plus 1 chi square 2 is equal to 8. Therefore, chi C2 square is 8 minus 4 is equal to 4. Thus, the possible only when chi C2 in tau 5 is plus minus 2. Now, take the class corresponding to C4 and do the similar procedure. 2 into 1 square, 2 into plus minus 1 square, 2 into plus minus 1 square, 2 into plus minus 1 square plus 2 into plus minus chi C4 square. So, it is equal to 2 plus 2 plus 2 plus 2 plus 2 into chi C4 square 8. Therefore, 2 chi C4 is equal to 8 minus 8 is equal to 0. This is possible only when chi C4 is equal to 0 in tau 5. Now, take the sum class of sigma V, 2 into 1 square plus 2 into plus minus 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 sigma V square is equal to 8. That is 2 plus 2 plus 2 plus 2 sigma V square is equal to 8. Therefore, chi sigma V square is equal to 0. This is possible when chi sigma V is 0 in tau 5. Similarly, chi D is equal to 0 in tau 5. Now, the C4V character table looks as, that is, besides plus minus 1 for tau 2, tau 3, tau 4, we have in tau 5 2, 0, plus minus 2, 0 and 0. In order to find the character for C2 symmetry operations in T5, for this let us use Orthogonality character, that is how to check orthogonality by using the equation chi summation chi r into chi j r is equal to 0, and let us take tau 1 and tau 5. If we make use of this orthogonality checking, we get 1 into 1 into 2 plus 2 into 1 into 0 plus 1 into 1 within bracket plus minus 2 plus 2 into 1 into 0, 2 into 1 is equal to 0. 2 plus 0 plus minus 2 plus 0, 0, 0. This is possible only if we take minus sign before 2 so that the sum is 0. Let us now check the orthogonality of T4 and T5 irreducible representation, which is given over here. 1 into 1 into 2 plus 2 into plus minus 1 into 0, then plus 1 into plus minus 1 into minus 2 plus into plus minus 1 into 0 plus 2 into plus minus 1 0, that is again it is 0. The product under C2 must be of negative sign, and chi C2 in T5 is already minus 2. Therefore, chi C2 for C2 in T4 should be plus 1, so that the result is 202000. The C4V character table now looks like this. That is, we are able to decide some of the characters, and we have to find out the rest of the characters for tau 2, tau 3, tau 4. Now, let us check orthogonality of tau 2 and tau 5. Here again 1 into 2 plus 2 into plus minus 1 into 0 plus minus 1 into minus 2 plus 2 into plus minus 1 into 0 plus 2 into plus minus 1 into 0, that is 2 plus 2 plus minus 2 plus 0. In order this equation is valid, the product under C2 must be of negative sign, and chi C2 in T5 is already minus 2. Therefore, chi C2 in tau 2 must be plus 1, so that the result is 2 plus 0 plus 2, 0, 0. Similarly, chi C2 in tau 3 is plus sign. Since there are 8 operations in the group, 4 of these must have chi is equal to plus, and other 4 must have chi is equal to minus 1, so that orthogonality rule is obeyed by all these irreducible representation tau 1, tau 3, tau 4, etc. The remaining characters may be written as plus or minus 1 in tau 2, tau 3, tau 4, so that these 4 have 4 plus and 4 minus 1. This is possible only in this way, that is, this shows over here, that is tau 1, tau 2, tau 3, tau 4, etc., and these are the various values ultimately have been obtained and put down, that is 4 ones are positive and 4 ones are negative, where A1, A2, B1, B2, E are Mulliken symbol for these irreducible representation. Meaning of these irreducible representations we have already taken into account in earlier modules on Great Orthogonality Theorem. Base function for these irreducible representation has also been explained in earlier modules. After saying about C4V character table, let us now move to another molecule and let us try to construct character table for this point group. Let us construct character table for C2H point group, and let us take 1,2-trans dichloroethylene. The various symmetry elements in these molecules are shown in the figure over here. Now let us work out characters for irreducible representation for C2 point group. This point group has E operation, C2 operation, sigma H operation and I operation. that is there are 4 symmetry operations. Therefore, the order of the group H is equal to 4. Each operation belongs to separate class. So, according to rule of great orthogonality theorem, there must be only 4 irreducible representation in C2H point group. And I just say let these be tau 1, tau 2, tau 3, tau 4. And let the dimensions of these be L1, L2, L3, L4 respectively. According to great orthogonality rules, these irreducible representations should satisfy the equation L1 square plus L2 square plus L3 square plus L4 square, that is equal to 4. This is possible only when we take L1 is equal to L2 is equal to L3 is equal to L4 is equal to 1. That is, all irreducible representation are of dimension 1. In a group, there is always one totally symmetrical representation for which characters of all symmetry operations in a class are plus 1 only. The characters of E give the dimension of irreducible representation. So, character for E in all these irreducible representation will be plus 1. The format of the character table for C2H point group looks as C2H point group, then we have tau 1 for which all characters for all symmetry operation in classes are 1, 1, 1, 1, and also character for E are 1, 1, 1, 1. This is the format of the character table. Now, we have to find out rest of the characters of this. Great orthogonality theorem demands that the remaining 3 irreducible representations will be orthogonal to this totally symmetrical irreducible representation. Thus, according to great orthogonality theorem, all other irreducible representation tau 2, tau 3, tau 3 must be orthogonal to tau 1. These remaining tau 3, tau 4 representation will have character as either plus for 2 symmetry operation and minus 1 character for other 2 symmetry operations of C2H point group. So, to satisfy the orthogonality condition. Thus, for C2H point group, the 4 irreducible representation will have character, that is tau 1 all are positive, tau 2 1 1, then minus 1 minus 1, tau 3 1 minus 1 minus 1 and 1, tau 4 1 minus 1 1 minus 1. That these characters are correct or not can be verified by checking the orthogonality of tau 1, tau 2, tau 3 and tau 4. Let us check the orthogonality of tau 1 and tau 2. 1 into 1 plus 1 into 1 plus 1 into minus 1 plus 1 into minus 1 is 0. That is, tau 1 and tau 2 are orthogonal to each other. Orthogonality of tau 1 and tau 3, 1 into 1 plus 1 into minus 1 plus 1 into minus 1 plus 1 into 1 is 0. That is, tau 1 and tau 3 are also orthogonal to each other. Orthogonality of tau 1 and tau 4, 1 into 1 plus 1 into minus 1, 1 into 1 plus 1 into minus 1, 0. It means tau 1 and tau 4 are orthogonal to each other. Orthogonality of tau 2 and tau 3, 1 into 1, 1 into minus 1 plus minus 1 into minus 1 plus minus 1 into 1, 0. Tau 3 and tau 4 also 1 into 1 plus minus 1 into minus 1 plus minus 1 into 1 plus 1 into minus 1 is equal to 0. It means tau 3 and tau 4 are orthogonal to each other. Like this, we can verify the orthogonality of all the irreducible representation tau 1, tau 2, tau 3, tau 4. Some of these orthogonality have been checked. And now we have learnt various examples, that is C4V and C2H. For character table you can work out other character tables also. Constructions of character table C4V point group has been explained in detail with example at each and every stage of the process, and xenon oxytetrafluoride has been taken as the example which belongs to C4V point group. After the entries have been obtained, these have been verified. Verification of characters of the irreducible representation so obtained has been verified by following the rules of great orthogonality theorem. That is, in C4V, the various steps have been explained, each and every step has been shown, and we were able to find the complete character table of this C4V, except the basis function we have not taken into account over here. Now, construction of character table for C2H point group has been also explained, and by taking suitable example of trans-dichloroethylene and the various symmetry operation into this, and we have obtained the character for tau 1, tau 2, tau 3, tau 4. All are one dimensional irreducible representations, and whether these are correct irreducible representations have been verified by checking the orthogonality of tau 1, tau 2, tau 3, tau 4, and it has been found that the entries which have been obtained are correct. Now, after entries of these correct entries, we can also check all other rules of great orthogonality theorem. Now, with this we can construct other character tables also.